introducing that my 4-bit adder is working properly, right? So this is what we got done. Now the next thing is continuous assignment. So from this point onwards, we'll see what are the different ways we can write a Verilog. There also we'll start working with data flow modeling, structural modeling, behavioral modeling. So in that, what are the things available? What that means, what are the logics that we need to follow? What are the syntax that we need to follow? That will be covered. So if any of the any kind of a Verilog code that we are implementing or we are designing, we should have either of continuous assignment, structural modeling, or behavioral modeling, right? So we can use any of it depending upon our requirement. So unknowingly also, what we have done as of now, we are using continuous assignment. So why? How we have used continuous assignment? So those things we'll be discussing. So today we'll be focusing on continuous assignment and Verilog operators. So if you remember, while we are providing Boolean expression, we are using some XOR gate, OR gate. Most of the people were a bit confused. This basically is C only, just what that each and every bit identifies, what are the different types of Verilog operators available, if how we'll have some use cases of it, that means some examples of it. All those things we'll be doing in today's session. Okay. So if you remember, we are using assign statement. So what is this assign statement? Under which modeling style this assign statement comes into the picture? How to use this assign statement? Those things we'll see. And how to provide a delay. That is called hash delay. This is our simulation delay. So the concept of delay will also introduce. Right? So now it comes in, there are two, we know there are three ways basically. So we have gate level. So this is fully structured. Inside behavior, we have data flow modeling, behavioral or procedural modeling. So this two things comes under behavioral modeling. So what behavioral modeling is? We'll see the specification. Depending upon the behavior of the circuit, we can write a equation or we can write a step by step, like you can write is not step by step. We can deduce the logic and we can write some code out. We can write the code in an algorithmic manner. So there are two ways. So one way is data flow modeling. So data flow modeling, remember, we are using Boolean expressions and operators, right? So all those things comes into data flow modeling. So all for those things, if I am directly using data flow modeling, we should use assign statement. So that's why assign statement is required, right? So here what happens, the data assignment to the output is continuous. That is the main point that we need to remember. So that means when I'm using assign statement, the right hand side, that means the value that will be evaluated should be, that is the left hand side, I guess. Yeah. So this should be of net data type. And the expression, the variables and the wires in that expression can be of net or reg data type. That means where or reg. Because inputs can come at any time or it can come at certain events. Both are fine. But the assignment to this variable, to the output variable that it has assigned statement should be of net data type or wire data type, because it is continuously evaluated. This is the first thing that we should do. Behavioral modeling will be done in algorithmic manner. That will take it up after completing data flow and structure, because data flow and structure are very basic. When we start Verilog coding, we'll start with data flow and structure. But what we'll be doing eventually, we'll be working with behavioral modeling, because when the chip complexity, when the design complexity grows, I cannot write all the, I cannot convert all those design into Boolean expressions, right? For simple logic, I can convert. For bigger logic, it will be difficult. So what I am doing, what I will be doing is, for simple logic, let's say for some glue logic, or you can say certain modules are there from their few inputs are coming. So for that, I can use data flow model. For structural modeling, for yes, yes, please.
Sir.
Yeah, yes, yes, please. Screen is not visible. Screen is visible. 1 second. Okay, wait, somebody has shared. Okay, fine. Is it visible now?
Yeah, now it is visible, sir.
Okay,
Yes, sir.
fine.
Sir, one small thing, sir.
Please,
Sir,
sir.
as you are saying for net and wire, so when there's a connection between two gates, we can term that one as in wire. Okay. But how to differentiate net over there? For example, as you told that as when data are changing, we can use net and wire. But when data are not changing, we can go for a SIN statement.
No.
So how to differentiate between net and wire again?
Net is a data object. Inside net, there are multiple data types. So where is a net data type? Right? Similarly, we have wire and I'll provide this material today. No worries. Wire or then, but wire and or tri-state logic, the FPGA or ASIC flow doesn't support. Only it supports wire. So we have to wire and net are same. Net is called the data object. Inside net there are multiple data types. From that wire data type I'll be using. Is it fine, sir?
Sir, if two gates are there, and if I'm defining a wire, as suppose gate 1 is having input A and B, output is Y, and the Y is going to gate number 2. So that output which is coming from as a output going to input, I'm defining that as wire T. So can I call that T as net also?
1 second. So A and B, one AND gate is there. It's Y, right? And then from
the
Y,
diagram which I've drawn, the Y is coming as the input to the next gate. So this Y is a wire. Okay. So
a Y
can I
wire
define
yes.
that wire?
Yeah.
So can I say Y is also net also? Is it?
Yes, correct. Both are same.
Okay, so there was a confusion with me that net and wire are different.
No. Listen, net, as I told, net is a data object. So inside net can be of various types, right? So net can be this also. But this thing is not different. This is wire and or wire or. But this thing, both for FPGA terminology, net for or ASIC, like for digital design, wire and net are same. So while writing the code, what we'll be doing, we'll be giving as output, or you can say wire, right? So we'll be giving wire Y. So that means it's a net data type.
Okay, sir. Thank you.
Okay. But the thing is that while using assign statement, we should always give wire, or you can say net data type, because it is continuously evaluated. Correct? So this is what we need to come up with, right? So you can, yeah. Okay. So what we are doing as of now, yesterday and day before yesterday, we are modeling combinational logic. So easily you can model combinational logic using this continuous assignment, that is assign statement. Right? So I can say it drives the values onto the net. So wire and net we can change interchangeably, because inside net we have only one data type that will be used in FPGA and ASIC flow, that is net data type. That is wire, right? So that will be using. The assignment occurs whenever the right hand side value changes. So Y assign Y, A and B, let's say. So what does it mean? Whenever whenever B or A changes, this statement is evaluated, and what will happen? We'll get a AND gate which will give me the AND function, and that particular value will be represented by Y. So this is what will happen, right? So it is continuous assignment, right? As a net declaration statement, as so it is a continuous assignment, right? So first of all, we need to declare Y as net variable. That means you can that is net variable is basically where, and we have to use this assign. So this is about continuous assign. So this is the syntax. So you can see here assign. This should be a wire. You can see here output 1 has been defined as wire. It should not be a reg. So if I refer as reg, the Vivado will give me error. Directly it will error. It will say that this is not allowed. Then A is
why sir?
Why, sir? Because
why?
Yeah. Yes, please.
Wire and net both are same, no sir. That is confusing.
So I am telling a reg. Net I am not giving. Net you cannot write.
Okay.
Net is a data object. Inside net, wire I am using. I am telling about reg.
So wire I can write.
Only wire is allowed.
So can I write net over here, net out A and B?
Net doesn't have any meaning. So net actually what happens whenever I am synthesizing a code. So those where is regarded in the synthesis netlist, it is named as net. Correct? So that will like coincide with our code. So we cannot write net. So net has a special meaning over there in the netlist. So we should write where.
Okay, sir. Okay.
Okay, fine. Yeah. Reg we cannot define because reg is evaluated at a particular event. So that the meaning of assign won't come. So that's why the continuous assignment won't be coming. So reg is not allowed, right? So here it can be operands, and this will be an operator that will be defining now, and this operands can be of where or reg data type, both, right? So A can be of reg and B can be of where, or both can be reg or both can be where. So that option is available. But on the left hand side, it should be always of where, that is of net data type, right? So this is the only thing that we should remember when we are working with continuous assignment statement, that is data flow modeling. Data flow modeling, generally most of the time what we'll be doing, we'll be taking a Boolean expression, we'll be using assign statement, and we'll be developing the code, right? So what we can do, there are two ways. I can use where out one, then I can use assign statement, or I can use where out one equal to a and b. So both can be used alternatively. By default, since I am using this statement, the tool knows there is a by default there is an assign statement over there. So if you don't want to write assign keyword also, that is also fine. But generally in industry this method is used. Otherwise, you might get confused with other modeling styles. So that's why better to prefer this. So you declare the data type as where for what out one, then you use the assign keyword. Then again you call say the variable name, then you give the Boolean expression. Right? So this is how to work with assign statements, that is data flow model. Okay? So you can see here. So directly here, now what is the change in the code? Yesterday also what we did, we worked with 4-bit ripple carry adder, right? So what we did, we gave input and output module. Then I have instantiated 4 full adders, and using those full adders, I have created a code. Why? Because let's say I want to use full adders, but now that concept of operators comes. But we have this plus operator, this plus sign, right? This plus sign is there. So if I give plus sign, what will happen? So if I'm giving plus sign, why I'm combining C out and sum into one kind of why I'm putting it into brackets, right? So many questions will come. So that questions will be answering it in Verilog operators. So we should know how many operators are there so that I can use directly some operators which we can easily use. So yesterday's lab, what we can do, we don't need to instantiate also if we have knowledge about this operator, this plus operator. So plus operator it will add. So this plus has a special meaning in Verilog, that basically it will add a plus b and it will generate certain hardware. But here what will happen, the tool, the synthesis tool will interpret as a carry look ahead adder. So in carry look ahead adder, what happens? The carries are calculated separately and the sum is calculated separately. But in case of ripple carry adder, the generic adder, what we have done, the carry and the carry data and the sum data are calculated one by one, right? So what happens in ripple carry adder, it's a bit slower than the carry look ahead. Since I am targeting to 7 series FPGA, since I have selected 7 series FPGA, if I am using this plus option, the tool will think that it is a carry look ahead adder because it has the architecture it has carry look ahead adders, it has dedicated carry chains to hold the carry, right? So those things we'll be discussing more when we'll be working on the FPGA architecture. But there are multiple ways to implement design onto the hardware. That is what we can go through. So, but here what we have seen, we are seeing different operators. So now we'll see one by one what are the operators that we have used and what are the operators that we will be using. Yes, yes.
So in this case, it will assign A and B the answer
Yes.
to the C out plus sum both. Is it so?
What it will do, since if you remember when we have combined A and B yesterday, when we have added, the output
Yes.
can be of 5 bits.
Yes.
Yeah. So what it is doing, this operator is called concatenation operator. So it is combining both sum and cout into one bus. So sum is already a bus. It is of 4 bits. Cout is of 1 bit. So it is combining into a 5-bit bus using this concatenation operator. So we should know that's why what this operator does. So that is what we'll be doing now, right? Okay. Yes. Yes, sir.
Fine.
Okay, okay, fine. So this example we have done. So this examples, what we have done is actually data flow modeling, right? Okay. So this is also a same thing that we have discussed. This is also a data flow modeling tool, right? Fine. So this you can see it's a priority encoder. So what we need to do for priority encoder? So what happens whenever, depending upon the priority, here I3 has the highest priority. So if I3 is 1, and in encoder what happens, multiple bits can be high at once, right? So but we have fixed the priority, since we'll be using priority encoder mostly. We have fixed the priority to the MSB bit. So if MSB bit has the most priority, other I2, I3, I0 doesn't care. So what we'll be doing, I have generated valid signal. Depending upon a valid signal, this, since I3 is 1, so that means my coded output is 1 1. Similarly, if I2 is high, then 1 0. Similarly, if I1 is high, then 0 1. If I0 is high, 0 0. Right? That is fine. But if no inputs are there, that is all are 0, then so it is not a valid data, right? So that's why I have added one more signal that is valid. Using this valid signal, what I am doing, I am identifying that this data is only valid. So any of the inputs should be high. Then only I can say it is a valid data. Otherwise, it is not a valid data. So this is, don't care. I will not even look at that. So that's why you can see for valid data, this is the Boolean expression from the K map that we found. Then for Y1, there are two outputs, right? For Y1, then Y0. So I can give it multiple assign statements and you can work with that, right? So please try this example. You can take a screenshot and try this example on Grado. Try to simulate it, and we have to see the the logic of priority encoder is correct or not. So what we can do, we can have multiple inputs over here, and we can see the data. So basic priority encoder implementation we are doing, right? Fine. So finally, the thing is that still I know there will be confusions regarding this negation and or there will be double or in some ways. So where to use it, how to use it. So this will be discussing in our next topic, that is this one, operators. So here you can say one more data flow modeling I am telling. This is like an n-bit comparator, magnitude comparator, right? So this I have fixed parameter as 5. That means it is a 5-bit value. So I can fix that. So 5-bit value means the maximum bit will be 31. If it is 4-bit, it will be 15, right? So I'm comparing two 5-bit data, and my output is saying that it is A is greater than B, or it is equal to B, or it is less than B. So that value, the like that signal, the comparator is doing. So how to do that? So you can see here we should know. That's why we should know this operator. So here, if A is greater than equal to B, the value, so this will be 1, and the others will be 0. If it is A is equal to B, so this will be 0, this will be 1, this will be 0. So if it is 5 and 5 that I am doing, so it will be A equal to B will be high. Then if it is, let's say 6 and 5, then 0 0 1. So this is how the values will come, right? So like that you can practice certain examples of them. So this is a very nutshell idea about data flow modeling. But data flow modeling is never complete without understanding operators, because if we know operators, then only we can work with certain examples. We'll do that, right? But on top of that, let's say what happens. I need to talk about simulation games. Why? So let's say this is just an example. So all those things, it will be a bit trivial for you. That that will discuss in a subsequent topic itself. Just I will finish this slide. This is the last slide for this topic. So here you can see hash 3. So what is this delay? So let's say what happens when I'm implementing a ripple carry adder, or you can say um, a any kind of a logic, any kind of counters, any kind of registers onto the hardware. So what happens? So whenever it is implemented onto the hardware will have its own gate delay and net delay, right? Tau RC delays, the CMOS delays will be there, right, inside the gates. So it's like the electrical delays. So for that electrical delay, will not get the data at that instant only. There will be certain transaction delays. So if I want to model it onto simulation, because simulation won't understand the delay. So yesterday, if you have seen, we have simulated our design, right? At each and every sharp transaction, we are getting the output, but that won't be there in than actual hardware. So it will be after some time the values will come. So it will be like that, right? So if I want to model it in simulation, then I'll be using this hash delay. So hash delays, what it will do, it will be ignored during synthesis. These are not synthesizable. This equation is synthesizable. This is synthesizable, but hash tree is not synthesizable, because hash tree for synthesis, it doesn't hold in any meaning. Only to see in simulation, okay, I want to make a real kind of a circuit in simulation. So for simulation, I can give that particular delay. So this is called simulation delay. So it is given as hash, then the number, then certain number. So you can see this, it can be 3, it can be 5, it can be 4. So what it will happen is, if we give it here, so this will be evaluated at time 0, but this answer, like the value will be updated after 3 clock cycle. You can see here the value have changed, A and B value, but the value updated, the final value was updated here. So after 3 simulation time, that is 3 nanosecond simulation time, I am seeing the final value, right? So this is the idea about simulation delays. It is only used to have a in simulation to check the real like real world characteristics of it, this thing of a circuit. So anyways, when we'll be implementing, those simulation delays will be ignored in during synthesis. We'll be implementing as a hardware, but that hardware will have its own delay. So if we do post synthesis simulation, then we'll see certain in transient delay, that is the gate delay, internal delays of the gates of the LUTs, or the resources, you can say, will coming into the picture, right? So this is the idea about simulation, right? So with this concept, what we can do, so we'll have some Q&A. So can you tell me what is wrong in this example? By seeing the example, can you tell me what is wrong? There will be many things that we don't understand, but we'll just need to point out as per our understanding what thing is wrong in that example. So first thing I am giving an idea is CS. You can see here CS is declared as reg. So this won't work. Here the tool will give an error. So it should be of wire data type, right? So correct? Okay, fine. So yes. So this is the thing. Yeah, it should be of wire data type. So we have to write wire, right? So if we write wire CS, then this statement will be executed. So this thing we don't know as of now. So we'll not go to the depth. After completing data flow and structure, we'll go for this behavioral model, right? Then we'll take this answer again. Now the next thing, you can see here they have rectified it. Now what will happen? Is this code synthesizable or not? Will I get any hardware out of it if I synthesize it? Yes or no?
Yes, because it is saying read write now.
Yes, correct. So read write, some hardware will go. But what will happen to this hash delay? These are not synthesizable, right? So those delays will be ignored during synthesis. This delays will come in simulation only, but this will be ignored by the synthesis tool. So the synthesis tool will just skip those delays, because if those delays doesn't have any meaning for the synthesis tool, right? Okay. So we got an idea about the data flow modeling. Now the main thing is that how to logic that is using Boolean expressions. So in Boolean expressions, each and every Boolean expressions you have seen. Sir, can you please mute? Virendra sir?
Yes, sir. Yes, sir.
Okay, thank you. Okay. So the most important thing is the Verilog operators that we have seen, right? So how many operators are there? What is this operator precedence? All those things we need to have an identity, because if we know the operators, it is not only required to use basic AND gates, OR gates, all those things. What we can do using operators, can do many things. So we should know how to use operators. And Verilog operators can be used in both data flow modeling, it is extensively used, and also with behavioral modeling. We'll also see how to use Verilog operators with behavioral modeling. So that will be very much important when we'll be going ahead. So we'll see all the different types and classes of Verilog operators and how to work on them. So simple from arithmetic examples, bitwise examples, logical examples, all those things we'll be doing, right? Okay. So how they have done is in Verilog they have segregated, they have made a group of operators. First of all, this bitwise operator. Bitwise operator we know, right? We have this is negation is NOT gate. Then we have AND gate, XOR gate. So these are all bitwise operators. So for that we will be needing ampersand is AND, XOR is this the hidden symbol right there. Then we have logical operators. Logical, it will see the logical equivalence out of it. So we have relational operators, equality operators. Then most of the operators are same as in Verilog, but there are certain differences. Like this reduction operators is new. Then conditional operators are basically, we'll see what is this conditional operator. This is also new. Concatenation operator, as I told, it can be multiple bits. It can combine into a bus. This replication operator also, it can replicate multiple bus. There's shifting operators also. Basic shifting we know, right? Left hand side shift of bits, right hand side shift of bits. But there is arithmetic shift operators also. That also we'll see. And then we have arithmetic, this one, arithmetic logic, like plus, minus, all those things. So division, all those things. So we'll see now which operators are used and how to use. But the thing is that, as I told, we are dealing with Verilog HDL, so hardware description language. So that means all those operators may or may not be synthesizable. Some operators are synthesizable, some operators are not synthesizable. Those also we need to take care of. So we should know when I'm writing a code, this operator is synthesizable or not. If it is synthesizable, then only we'll get a hardware. Otherwise, we won't get a hardware. So those things we need to have a look at, right? So first we'll start with bitwise operator. So bitwise operator, we know for all those basic gates, we have an operator. So this is for AND gate, this is for NAND gate, this is for OR, this is for NOR, this is bitwise, that is negation, this is XOR, and this is XNOR. This is very basic, like in basic C program also, the same operators are used. So what happens in bitwise operator, it will take 2 bits at a time, right? It has 2 operands you can see here, except this negation, it will take 1 bit at a time. So that means this operation will be performed bitwise, one by one, like one by one operation. So if I have a bus also, let's say 1 1 1 1, I want to end it with 0 0 0 0. What will happen first? This will be performed first, then this will be performed, then this, then this. So bitwise data will be performed, that will be worked around with sorry, yeah. So
हेलो
yes, sir.
हेलो
Okay. So bitwise
हेलो
performed. So let's see some examples.
अरे तो कह रहा हूँ कि टिकट कंफर्म हो गई। अरे कंजर कंफर्म हो गई, पापा की कंफर्म हो गई, एक टिकट बोला था ना कंफर्म हो गई, लिख लो। हाँ जो एक ही हुआ ना, आपके आपकी भी सीट कंफर्म ही है, लेकिन आपकी आधी आधी सीट है। क्या बोल रहे हो? हाँ तो कोई नहीं, आप दोनों एक सीट पे हो जाना, कोई नहीं। हो गया ना, कंजर ही कहेंगे पागल कर दिया, सुबह से क्लास भी लेने नहीं दिया पगली। है, अब बोलते नहीं हो। हाँ ठीक है, का S4 है ना, आपका S4 में 48 है, पापा का 15 है। हाँ तो एक ही सीट पर दोनों जने हो जाना ना। ठीक है, कंजरी कहेंगी, पागल कर दिया, पागल ही कहेंगी। खुद तो है ही है, मेरे को भी पागल कर देती हैं।
I want to use full adder, but this is called concatenation operator. So, yeah, and my output is saying that it is A is greater than B, or it is equal to B, or it is less than B. So that value